What this means is if you start with reactant A and perform a chemical reaction to make products B, if the enthalpy change for this reaction was negative 10 kilojoules, if a second route was taken to take the reactants A and convert them to products B in 2 steps, route 2, the overall enthalpy for the reaction would be negative 10 kilojoules. Hess's law states that the enthalpy or heat change accompanying a chemical reaction is independent of the pathway between the initial and final states. So here's another example. Direct conversion. This reaction, negative 890 kilojoules, 2 steps, overall change in enthalpy is the same. Here we have 3 equations. These 3 equations add up to the final equation here. You will notice in the final equation there is only reactants A and R and products K and T. That's because chemicals B, C, D, and G all cancel out. What that means, B is found as a reactant in the first chemical reaction. It's found as a product in the second chemical reaction. Therefore, chemical B cancels from the equations. Chemical C is found as a reactant in the second equation. It's found as a product in the first equation, so then it cancels out. Chemical G is found as a reactant here. It's found as a product here. It cancels out. Chemical D, found as a reactant in the third equation and a product in the first equation, so it cancels out. Then what's left behind is A, R, K, and T. Adding up the chemical reactions, you get AR converts to K plus T. Then adding up the individual enthalpies will get you the overall enthalpy for this chemical reaction. Here's another example where adding 2 chemical reactions equals a third. So I see this chemical as a reactant and as a product, so it cancels out, leaving behind Fe. These 2 chemicals are both found on the reactant side, so they add up to 3/2 or 1.5, and then the product. Adding these enthalpies, so we're going to practice an example of Hess's law. Here is a chemical equation that we need to determine the enthalpy change for, and we're given 2 chemical equations with known enthalpy values. Since I'm going to have to add these 2 equations to create this overall chemical reaction, I have to notice where the individual chemicals are positioned as either reactants or products. And what I'm noticing is lead chloride here is a reactant, and in this first equation it's found as a product. So what I need to do is flip this first equation. So what I mean by flipping the equation is writing it backwards. You can see how this equation was then written like this. In flipping the equation around, what changes with the enthalpy is the sign. As when lead reacts with chlorine to form lead chloride, it's exothermic. But if lead chloride was to break down to lead and chlorine, that chemical reaction would be endothermic. In the second equation, I noticed that lead chloride here, lead 4 chloride, is found as a product in the overall chemical reaction we're solving for. So I don't need to flip this equation. Now that we have these two equations, lead is found on the reactant side and product side, so it cancels out. 1 chlorine is found on the product side. 2 are found on the reactant side, so 1 is left over. Then you have an overall equation, PbCl2 plus 1Cl2 makes PbCl4, which is the equation we want to determine the enthalpy for. So then we just need to add these two values together and we will get the enthalpy change for this overall reaction. It is 31.1 kilojoules. Questions?